Very good evening. Today we'll start our class 18 and I'm going to talk today mainly steady state heat conduction through cylinders and spheres. In the last class we covered steady state heat conduction through composite walls and derived the expressions. So we will focus our talk today mainly on cylinders and spheres. So it's a different geometry. So let us see what happens when heat transfer in the one-dimensional heat transfer happens through cylinders and spheres. So you can see here cylinders which are having internal and external radius. So it's in hollow cylinders. The internal radius is given by R1s. Here you can see this is R1s. And this is external radius given by R2. If we assume the inside temperature Ts1 is hot, so let us assume some hot fluid is flowing through inside and outside is at the atmosphere or some cold fluid. So obviously heat is going to transfer in the radial direction. So there will be heat flask in the radial directions that we are going to determine. Okay. So what we have done, that we have considered that length of the cylinder is capital L. The inside temperature is Ts1 and outside temperature is Ts2. And it has been given here. You can see the cross section has been drawn here. You can see Ts2 and Ts1 and Ts2 because Ts1 is greater than Ts2. And this is the radial direction is R. You can see it is hot fluid and cold fluid given, right? So if you consider steady state heat conduction with no heat generations, we can write it as per Fourier's law, the heat flask QR is equal to minus Ka dt by dr. Why dt by dr? Because the dx, the thickness of the wall which we consider when heat conduction happens through composite wall, it will be replaced by dr. That is the direction, radial direction, right? The radius in the radial direction here, right? dt by dr, because the heat transfer happening here over a minute distance of dr. Here the area can be given by 2 pi RL because that is the surface area over which it is being transferred. So that can be given by area minus k 2 pi RL by dt dr. Where dA equal to 2 pi RL is the area normal to the direction of heat transfer. Now what you can see this that equations, the quantity k by r dt by d is equal to 0, which is actually independent of r, that is the radius. So the heat conduction, the conduction heat transfer of rate, that is QR, in this equation 9 is constant. Actually it is constant in the radial direction, but the flask which is not constant but varying in the radial direction, right? The total amount of it constant, but the flask is not constant, which is actually varying in the radial direction. So how we will determine this equation? We can set the boundary condition like we can say R1 and R2 and then integrate this dr by r, and then the temperature will be Ts1 by Ts2, or else we can solve it for two different equations. We can, if we just solve this differential equations, then you finally get Tr equal to C1 ln r plus C2. And as I said that how to get this constant integration constant C1 and C2, you can use the following boundary condition, that is Tr1, that is at the when radius r is equal to r1, T is Ts1, T is equal to Ts1, that is the inside temperature, and r equal to r2, T is Ts2. So if you plug this value and solve for C1 and C2, to get the expression becomes like this: Tr Ts1 minus Ts2 divided by ln r1 r2 plus a times ln r by r2 plus Ts2. Now this substitute this equation into 9, that is the previous equation, then you solve for it. You can get QR, that is the heat flask, equal to 2 pi Lk Ts1 minus Ts2 divided by ln R2 by R1. So this is the equations for heat flask in the radial direction for a cylinder. So what will be the R, that is the thermal resistance. If you remember that R is nothing but it was L by K. So similarly it will be this quantity divided by this quantity. So it will be ln by R2 by R1 divided by 2 pi Lk. So that is actually thermal resistance for heat conduction through cylinders. Okay. I hope you understood this. Now let us look into cylinder problem, but if you have different radius in the direction, as you can see, it has been given here. Similar thing is happening, hot fluid flowing inside and then outside surfaces at cold or atmosphere. But here instead of two radius, here are multiple radius which are having a temperature, a different temperature and different direction. Like, so actually inside temperature is given by T infinity 1, then gradually temperature decreases, right, as it comes to the surface. And then you can see the radius is R1, R2, R3 and R4, ABC, right? So R1, R2, R3, R4, there are four different radius which are having a different temperature, TS1, T2, T3 and TS4. And the inside hot fluid which is flowing actually having a temperature of T infinity 1. And if you consider that is instead of some, it is a convective heat transfer, then it is the convective heat transfer given by H1. So T infinity 1 is the temperature inside and the convective heat transfer coefficient H1. Similarly, the outside temperature is T infinity 1 and the convective heat transfer is given by H2. So actually you can see there are 1, 2, 3 and 4, 5. There are total 5 resistance which can be given into the higher type of circuit, right? VI circuit. So each resistance will offer each layer will offer some sort of thermal resistance which can be given by, because since it is the convective heat transfer, so it will be given by 1 by H1 2 pi R1L because the radius is R1. Similarly, next two layer will be given by ln R2 by R1 2 pi KAL, where Ka is the thermal conductivity of this second layer, right? Similarly, third layer will be ln R2 R3 by R2 2 pi KB by L, right? In last one, ln R3 by R4 by R3 by 2 pi Kc by L, and finally 1 by H2 2 pi R4L, which can be written here. You can see this formula has been written here, right? For an overall heat transfer coefficient, instead of this, if you consider the overall heat transfer coefficient, then you can write T infinity 1 minus T infinity 4, here infinity 1 and then infinity 4 by R total. So R total will be this term, right? The denominator will be R total, which also can be written in this form, which is overall heat transfer coefficient U into A, T infinity 1 minus T infinity 4. U is defined in terms of inside area A, 2 pi R1L, then UI will be, the UI mean in overall heat transfer coefficient based on the inside radius, then it will be 1 by Hi plus R1 by Ka ln R2 by R1 plus R1 by Kb ln R3 by R2 plus R1 by Kc ln R4 by R3 plus R1 by R4 1 by H4. I hope you understood this. Just replacing this term and then we are considering the area as 2 pi R1L. So just take this 2 pi R1L and then this term will become U. And the overall heat transfer coefficient also can be written UI U1 by A1 if you have inside radius A1 and overall heat transfer U1, and then so on, right? Most important is this equation and this equation. This is R and this is UI 1 by R, right? So let us look at some solved example to understand the problem in better way. So here actually you can see the thick walled tube of stainless steel with 20 millimeter inner diameter and 40 millimeter outer diameter is covered with a 30 millimeter layer of asbestos insulation. So there are three layers. The asbestos insulation having a thermal conductivity 0.2 watt per meter C. Now, if the inside wall temperature of the pipe is maintained at 600 C and the outside insulation is at 1000 C, calculate the heat loss per meter of length. Okay, it's a very nice problem. Inside radius given, diameter given, so you can calculate the radius 10 millimeter, and then similarly outside radius given 20 millimeter. Now let us graphically look in this problem. There are three layers. Inside there is a stainless steel which is having 600 T. We can consider it T1, and the inside radius is R1. Then the second one is the R2. So R1 plus this thickness will be R2, and then finally the last one is R3, that is R1 plus R2 plus this thickness. So inside is stainless steel. This is given here. Then it's asbestos, and finally atmosphere, right? So we are considering this is 600. We are considering this is at T1 and then at T2, right? And then finally T3 is 1000 C. So inside temperature 600, then this is T1, this is T2, and then T3. Okay, I hope you understood this problem. So R3 will be how much? R3 will be the thickness of this, right? The thickness is given 30 millimeter asbestos, so it will be R1 is already calculated 10 meter. R2 you calculated 20 millimeter, that is outside diameter 40 millimeter given. Yeah. So it will be 20 millimeter, and R3 will be 20 plus 30, that is 50 millimeter. T1 given, T3 given, KB also given, the asbestos. So heat transfer per meter is 2 pi L T1 minus T3 divided by, now there are two layers, so it will have having thermal conductivity difference. The first layer will be ln R2 by R1 by Ka and plus ln R3 by R2 by Kb. I hope you understand this equation. Since the thermal conductivity of stainless steel is not given, you cannot see thermal conductivity of stainless steel. Therefore, we will neglect the resistance offered by the stainless steel to heat across the tube. So we are considering that thermal conductivity is negligible because it's not provided. We are considering it because stainless steel is highly conductible. So hopefully there will be no heat loss. So we can consider the second layer only. Okay, ln R3 by R2 Kb. First layer can be neglected. R3 you know, R2 you know, Kb you know, you put this value and then you know T1 and minus T3, then you can calculate minus 548.57. Now why it is negative sign? Because you can see here heat transfer happens from radially inwards. Okay, because of the insulations, it is not losing outside. You can say it is actually happening inward direction. Okay, that is why it is the negative sign comes. If it was positive, then you can see it is lost to the outside. Let us look into another example. A pipe thermal conductivity given 180 watt per meter C, having inner and outer diameter 80 millimeter and 100 millimeter respectively, is located in a space at 25 C. Very good. Hot gases at temperature 160 C flow through the pipe. Neglecting surface heat transfer coefficient, that is convective heat transfer coefficient. Calculate the heat loss through the pipe per unit length, the temperature at a point halfway between the inner and outer surface. And number 3, the surface area normal to the direction of heat flow, so that the heat transfer through the pipe can be determined by considering materials of pipe as a plane wall of the same thickness. So actually it is saying that the last case, you can, if you just assume this is a plane wall instead of a cylinder, then what will be the heat transfer through the pipe? So let us look in the first determine, let's see what are the parameters given. R1 given, that is the inner diameter 40 millimeter, R2 given 50 millimeter, outer diameter RO given 50 millimeter, hot gas temperature given TI 160 C because hot gas is flowing inside, right? And temperature of space in which pipe is located, this outside temperature given 25 C. The thermal conductivity of the pipe is given 180 watt per meter C. So actually heat loss will be Q delta T by R, right? Simple equation, right? Delta T is the thermal temperature difference, R is the thermal resistance. So 160 minus 25 ln RO minus divided by Ri 2 pi KL. Per unit length, so L will be 1. 160 minus 125 temperature difference, RO and Ri you know, and then you calculate, right? So actually heat loss to the outside, right? Not negative sign, so actually heat is flowing outside. Now temperature at a point halfway between the inner and outer surface, we have to determine. Radius at the halfway will be, what will be radius? That is the arithmetic division, right? Arithmetic average. Inside and plus outside by 2, that is 40 millimeter or 0.045 meter. Now thermal resistance of the pipe up to its midpoint will be R ln R by Ri divided by 2 pi KL. R is 45 millimeter, Ri you know 40 millimeter, 2 pi KL, then it will be this much thermal resistance. The same heat flow through the each section, because heat flow is same, right? Only heat flux is changing, I mentioned. The amount of heat flow is always changing. So you can say that total amount of heat flow will be same, Ti minus T divided by 1 point, that is the thermal resistance of this, right? Temperature difference, this equation only. And you can calculate that it's T and then solve for its T, that will be 88.7. Alternatively, you can also, using this equation, you can solve for it. You can see that this is a T minus Ti, T2 minus Ti equal to ln R by Ri, ln RO Ri, because you know heat flow is same. So you can just do the average one and then solve for it and you get the same answer, 88.74 centimeter. Now for the surface area normal to the direction of heat flow, so that the heat transfer through the pipe can be determined by considering material of pipe as a plain one, right? So we have to determine the log mean area. I'll discuss this log mean area for cylinders, all these things in the next class. Today I did not include these slides, but next class I'll mean. Just remember arithmetic mean area, log mean area is given by outside area minus inside area divided by ln AO minus AO. Just like that. So AO is 2 pi L RO minus RI because AO is 2 pi L RO. So 2 pi L is common for both. So 2 pi L RO minus RY divided by ln RO by RI. So you solve for it, the arithmetic logarithmic mean area. You get 0.2816 meter square. Now check Q will be how much? K arithmetic mean Ti minus TO RO minus I. So you put this value and then you solve it, it's same, right? 684288, which is approximately same as the calculator. So minimum thickness of insulation will be 82.76 minus 40. That is the, because 82.76 was the what is 82.76? I have to check it actually what I have done here. So you solve for arithmetic mean area, then solve for Q, which is say as a calculator. So what is being asked? The surface area normal to the minimum thickness. I think maybe it is mistake. I'll see this, but this is the answer. Okay. Surface area normal. This is the surface area. This is all validated. So this the third one is this one is the answer. 0.2816. Anyway, I'll see this. What is minimum area of thickness of insulation? One more problem. A steam pipe inner diameter given 150 mm and outer diameter 160 mm, having thermal conductivity 58 watt per meter C, is covered with two layers of insulation of thickness 30 mm and 50 mm respectively, and thermal conductivity 0.18 and 0.09 watt per meter C respectively. The temperature of the inner surface of steam pipe is 320 C, and that of the outside surface of insulation layer is 40 C. Determine the quantitative heat loss per meter length of steam pipe and layer contact temperature. And if the condition of the steam is dry and saturated, find the quantity of steam coming out in 1 meter pipe, assuming the quantity of steam flowing is 0.32 kg per minute. So here actually you see there is a inside steam flowing inside diameter of 150 millimeter. Then there is a outside diameter is 160 millimeter. There is a two insulation. You can see the insulation A, insulation B is this one, and insulation C is this one, right? In first radial, the R1 is given 75 millimeter, R2 given 80 millimeter, right? R1 and R2, you can see that. What will be the thickness? First thickness is given 30 millimeter and 50 millimeter, right? So R3 will be 80 plus 30, that is 110 millimeter, and R4 will be 110 plus another 50, that is 160 millimeter. Inside temperature given 320 C. Outside temperature is given 40 C. K is given 58 watt per meter C. That is steel pipe, right? And then the insulation is given KB and KC. This is KB and this is KC. 0.18 and 0.09 watt per meter C. So what will be the quantity of heat loss and layer contact temperature T2 and T3 if we assume? Quantity of heat loss Q will be similar, 2 pi L T1 minus T4, that is inside temperature minus outside temperature. Then the individual thermal resistance, ln R2 by R1 by K, ln R3 by R2 by KB, and ln R4 by R3 by KC. K is 58, KB is 0.18, KC is 0.09. You know all this R2, R1, R3, R4, all this. So you put this value and then you get 296.5 watt per meter. Also Q will be the amount of heat flow same, right? So per layer it will be same, right? So you can equilibrate all these things and then you can solve for T2 and T3, right? So here first two equation they are solving for T2. Actually you can use this equation because you have already determined Q. So that Q you know, right? That is the amount of heat flow that is constant. So that you can take this and then solve for T2 is equal to 319.95, and then again you take this and then T2 you know, and then you solve for T3 which is 236.5. Now the next problem is if the condition of steam is dry and saturated, find the quality of the steam coming out of the 1 meter pipe. Assume the quantity of steam flowing is 0.32 kg per minute. So quantity steam coming out of 1 meter pipe, right? Let's say it's in X. Total heat of steam when it is saturated at 320 C is 2703 kilojoule per kg from steam table. That has not been provided. We actually from steam table. If it is, I'll give you if it is in the problem. Heat carried by the steam per minute after losing heat in the pipe 0.32 kg per minute is given, which is multiplied by the total heat lost by the which is getting from steam table, right? So you get 847.17 kilojoule per minute. So this is the amount of heat 0.32 HF plus XHF, right? And then you solve for X because you know all this value, right? HF and HFX. HF is 1463 kilojoule per kg and HFX is 1240 kilojoule per kg. Saturation, this is also get from the steam table, right? So you get solve for X and then you get 0.95. This is a little different, but again, if I give this kind of problem, I'll definitely provide you either the steam table or the data. Okay, actual data. Let us look this final problem and then we'll move to the next chapter, next part. Aluminium pipe carries steam from steam at 110 C, which is having the pipe thermal conductivity K 185 watt per meter C, has an inner diameter of 100 millimeter and outer diameter of 120 millimeter. The pipe is located in a room where the ambient air temperature is given 30 C and the convective heat transfer coefficient between the pipe and air is 15 watt per meter C. Determine the heat transfer rate per unit length of pipe. To reduce the heat loss from the pipe, it is covered with 15 millimeter thick layer of insulation, which is K 0.201 watt per meter C. Determine the heat transfer rate per unit length from the insulated pipe. Assume the convective resistance of the steam unit. So there are two parts. One is no insulation and the second part is with insulation. So let us first consider the first case where no insulation, only the inside radius and outside radius of 15 millimeter and 16 millimeter. Inside temperature 110 C, outside 30 C. It's very simple. R1, R2, you determine THF given, TCF given, thermal conductivity K given. Heat transfer coefficient between the pipe and the air is also given, right? This is the pipe and the air, 15 watt per meter C. So you just put the value, heat transfer rate per unit length, that is Q by L. So actually L will be 1 here. You can write Q equal to 2 pi L THF minus TCF by ln R2 by R1 K plus 1 by HCF R2. So this second term coming due to the convective heat transfer to the outside surface. Okay. So Q by L, I think the L is here typo. It will be 2 pi THF minus TCF divided by ln R2 by R1 by K times plus 1 by HCF plus R2. See, it is L not here because L is 1. 2 pi, then temperature, and then R2, R1, you know, K, you know, HF given, R2 given. So you solve for it, 451.99 or 452 watt per meter, right? So heat transfer rate 452 per meter. Now for the case 2 here, actually you have an insulation. There's an insulation layer. So every other parameters remain constant. R1 remain constant. Now R2 also remain constant 60 millimeter, but due to insulation R3 will change. Actually 60 plus 50 because the insulation is 150 millimeter. So it will be 0.11 meter. So all the other parameters remain same, Ka, Kb, and KHCF. So actually, then if you put this value, there will be due to insulation extra layer coming. See here, this Kb term or not here because this is coming due to the insulation second layer, right? This is pipe and then this dotted layer. This is the insulation layer. So all the value again is known. Only the insulation will come here. Insulation parameter will come here. Then it's all. So it will be heat transfer rate per unit of insulated pipe is 138.18 watt per meter. So I think you can see due to insulation, the amount of heat loss decreased. It was 452 watt per meter. Now it is 138. If you put some sort of insulation, heat loss can be minimized. That is what I try to convey through this problem. So you please go through this slide and then you understand. Now let us look into now the spheres. What happens when the heat loss occur? One-dimensional heat transfer happens with spheres, which is having inner diameter, inner radius R1, outside radius R2, and heat is getting transferred in the radial direction, right? So again, you can write this equation QR minus Ka dt by dr. But here the area will be, instead of 2 pi RL, it will be 4 pi r square because it's a sphere, right? So you can again, area EC 4 pi r square is the area normal to the direction of heat transfer. Again, you can use the proper boundary condition and then T1, T2, R1, R2, and then solve for it. And then you get QR 4 pi K TS1 minus TS2 divided by 1 by R1 minus 1 by R2. Thermal resistance can be given by this term divided by 1 by 4 pi. I hope you understand this. It's very simple, just like the previous one, the cylinder one. Let us look into another aspect, that is critical thickness of insulations for spheres and cylinder. Let us consider a layer of insulation which might be installed around a circular pipe, the cylinder, as shown in figure. The inner temperature of the insulation is fixed at Ti, you can see, and the outer surface is exposed to a convective heat transfer to infinity. From the thermal network, the heat loss will be 2 pi L Ti minus T infinity ln Rho minus Ri divided by K and plus 1 by Rho by H. This is for the convective heat transfer to the outside surface. Now let us manipulate this expression to determine the outer radius of the insulation Rho, which will maximize the heat transfer. The maximization condition is we have to take the first derivative of this. If you maximize dq by dRO, that is equal to 0, and then you integrate, differentiate this, and then equal it to 0. Then you solve for Rho, it will give you K by H. So that is the critical thickness of the H will be K by Rho. K by Rho, that will be the critical thickness. Rho is the outside radius and H is the thickness. I hope you understand. K is the thermal conductivity. So what is the critical thickness? K by Rho. Okay. For a sphere, it will be critical thickness. The critical will be 2K by H. You can again solve for this similar expression using sphere. You can integrate and then differentiate and then solve for it. K, you can get it. Sorry, solve for H, you can get it. This is a snapshot of plane walls, cylindrical wall, and spherical walls. Different parameter heat equation, temperature distribution, flux, heat rate, thermal resistance. I mean, whatever you have derived so far, you can, it's a snapshot. Keep it in mind, there is no thermal energy generation. You can look into it. Let us look some numericals for spherical problems. A spherical shaped vessel of 1.4 meter diameter is at 90 millimeter thick. Find the rate of heat leakage if the temperature difference between the inner and outer surface is 220 C. Thermal conductivity of the material of sphere is 0.083 watt per meter C. This is very straightforward problem. Temperature given T1 and T2 with corresponding radius R1 and R2. R1, R2 given 0.7 meter, R1 given 0.61 meter, T1 minus T2 differential is given 220 degrees. So just put this value Q equal to T1 minus T2 R2 by minus R1 divided by 4 pi K R1 R2. This is the expression for heat transfer through a sphere. And all the parameters you plug the value and then you get 1088.67 watt. Okay. Another problem, it's a semi-heavy. Determine the rate of heat flow through a spherical boiler. This you can see it's a spherical boiler. Boiler wall which is 2 millimeter in diameter and 2 centimeter thick steel, which thermal conductivity 58 watt per meter Kelvin. The outside surface of the boiler wall is covered with an asbestos, which is having a thermal conductivity 0.116 watt per meter Kelvin. The asbestos is 5 millimeter thick. The temperature of outer surface and that of fluid inside at R, 50 C and 300 C respectively. Take inner film resistance as 0.023 kilo Kelvin per watt. So R1 given. R1 is how much? 1 meter, right? Because it's a 2 meter is a diameter. So R1 is 1 meter. R2 is R1 plus thickness, right? Thickness is 2 centimeter. This is 2 by 100. So R2 is 1.02 meter. Thermal conductivity of the spherical boiler is given. The Kb is for the insulation of the asbestos, which is given 0.116. R3, the asbestos thickness. Finally, R2 plus R3, right? Which is 5 millimeter thick. So R2 plus R3, that is 0.025 meter. So it will be 1.025 meter, not 0.025 meter. It will be 1.025 meter. It's typo again. So Q will be H1 A1 Ty by C as the heat flow from fluid to inner surface by convection. Or Q equal to given by 2 T1 minus Ti 1 by Hi by A, similar, right? Where 1 by Hi is the inner film resistance. You can see this is having 3 problems. Inner is that steel, and then there's an insulation, right? And then hot fluid flowing from the boiler at 300 C. R1, R2, and R3 given. So the total heat loss given Qr minus T3, 1 by Hi by Ai, that is the convective heat transfer in the inside, plus Ti by Ti, R2 minus R1, 45 K, R1, R2, and then R3 minus R2, 45 kb, R2 minus R3. You put the value all this and then determine 4.581 kW. I hope you understand this is from the heat flow from the fluid to the inner surface. This is happening for this one. Inner flame resistance. Finally, another problem. A cylindrical tank with hemispherical end is used to store liquid oxygen at minus 183. The diameter of the tank is 1.5 meter and the total length is 8 meter. The tank is covered with a 10 centimeter thick layer of insulations. Determine the thermal conductivity of the insulation so that the boil off rate does not exceed 10.8 kg per hour. The latent heat of vaporization of liquid oxygen is given 214 kJ per kg. Assume that the outside surface temperature of the insulation is 27 C and that the thermal resistance of the wall of the tank is negligible. Heat generated is given, right? 10.8 into 240, right? Because 10.8 is the boil of that heat, 10.8 kilojoule per hour, right? So that is 2311.2 kilojoule per hour. You multiply this by the amount of total weight, right? Pressure outside the insulation and Ti is the pressure of liquid oxygen inside the tank. For the cylindrical section of the tank, since a cylindrical tank with a hemispherical tank, we first apply cylindrical tank 2 pi K L cylinder TO minus Ti ln R2 by R1. You solve for this, right? TO minus Ti. And the two spherical end, the equation will be like this. Again, this equation is like this. So you can equilibrate these two equations, right? And then you get this Q cylinder plus Q end, which is actually the total heat loss by the boiler. 2311 already determined, right? So you can plug, first we equilibrate these two, and then we know this total heat is equal to Q cylinder plus Q ends equal to Q boil. So you can substitute one parameters and you solve for Q cylinder, right? So you solve for this Q cylinder. Now from the given geometry of the tank, R1 is given 0.75, R2 given 0.85, length of the cylinder given 6.5. So substitution this value, you can solve for Q cylinder and you get it 515.44 joule per second. So if you get this Q and then you can get the K. Here is the K, right? So you have to ultimately determine K. So you include this value and you can determine K is equal to this ln R2 R by Ri TO minus Ti 2 pi L cylinder into Q cylinder. All these then solve for K, which is 7.522 to 10 to the power minus 3 watt per meter. This is little like cumbersome, but again you have to equilibrate the equation, then solve for Q cylinder, and then you have to put this value of Q cylinder and get the value of K.